I'm Ji-Eun Byun, and today I'd like to present about physics-informed neural networks. We are currently developing for traffic assignment optimization, but the title is a little bit misleading because it is a little bit different types of physics-informed neural networks from the conventional definition. So first, let us begin with the problem's definition. So we have this, our system of interest is a road network, and we want to evaluate the traffic flows on links by optimizing the user equilibrium. In other words, we perform the optimization by assuming that the users take their routes in a way to minimize their travel cost. On the other hand, we have this hazard scenario, so which might reduce the road capacity, and thereby the travel cost increases and users take detours to minimize their costs as much as possible. In other words, whenever the road capacity change, then we have to perform the optimization again, which is expensive. However, this is an issue when we want to evaluate the network reliability analysis, because when we perform, for example, Monte Carlo simulation, we have to generate many realizations of this road capacity, and this means that we need to perform optimizations as many times as the number of samples. To address this issue, we propose to utilize neural networks to predict flows from capacities. However, this neural network involves high-dimensional inputs and outputs, which make the training of this neural network very demanding. However, there is a very useful information that we can make use of, which is that the neighboring links are particularly confined together by this flow conservation node principle. In other words, at each node, these incoming flows and outgoing flows must sum to 0. And our question was that if there is any simple way to invoke this principle. And so we propose a physics-based neural network where the loss function is defined by these two terms. So first term is the conventional term that measures the prediction error, but the second term measures the residual flows at each node so that the predictions can be made in a way to satisfy the physics. So as a result, this second term directly engages this particularly dependent links, and as a result, it plays a role as filters, but in a kind of different way of these conventional filters that define filters by filter shapes, like convolutional neural networks or graph neural networks. And by doing so, we expect two effects. First, we want to enhance the exploration capability of the neural network by providing additional physics-based information. And second, the second term can be used for diagnostics of the predictions. In other words, if this second term remains high throughout the training session, then we might want to take a further action, like tuning the hyperparameters or increasing the number of epochs, because this means that our current neural network is not properly grasping the underlying physics. So this is our result for the road network that we saw at the beginning of our project, our presentation. And here we calculate the total travel time based on the predicted flow values. And we examined the two neural networks. First one is only the first conventional error term, and the second one with additionally with the residual error term. And we can see that for the training data, the predictions are made better for these conventional neural networks. However, when it comes to test data, the proposed neural network provides better predictions, particularly for these high total travel time region where the training data is scarce. And thank you for listening.